All right, so our next topic is mixed resistor circuits. We start with a definition, series and parallel circuits. So a series circuit is a circuit where resistors are connected in a row with no junctions in between. So in this first circuit, we see 3 resistors connected in a row, no junctions, not series. The second one, because of that junction, is not a series circuit. Let's do a quick example. Now, if we apply Kirchhoff's current law to this circuit, we see that there's no junctions, so we would expect the current to be everywhere the same. All of the current flow through each resistor is identical. Now for the voltage law, the total gain in the cell is going to be lost across the 3 resistors, so the cell voltage will equal the sum of the 3 drops. Now, next we'll do a little algebra to solve for the total or equivalent resistance of this circuit. Just adjust to give myself a bit more room here. That didn't work very well. All right, scratch that. Now, for the total resistance of the circuit, it's going to be, based on Ohm's law, the ratio of total voltage over total current. Now we'll use the result from KVL, substitute that in. Total voltage is just the sum of the 3 voltages, and that's still over the total current. Now, by the laws of algebra, we can write that as 3 separate fractions. And then we could substitute in the fact that the total current is the same as I1, is the same as I2, and substituting in for the total current is the same as I3, but each of those V over I ratios is exactly a resistance. That's resistance 1, that's resistance 2, that's resistance 3. So what we've shown is that the total resistance in a series circuit is just the sum of the 3 resistors. Let's try a quick example then. So we've got a 100-volt cell, a 5 and a 20 ohm resistor. And what can we say about the drop across the 20 ohm resistor? Well, because the 100 volts is lost across both the 5 and the 20, it's important to realize that the drop across the 20 is not all of the 100. Now, it's going to be more than half because the voltage drop is proportional to the resistance. In fact, you could use a ratio. It's 20/25 of 100 if you like. So that would mean 80 and 20 if you did it a ratio. But the point is that it's not all of the 100 loss because the 5 ohm resistor also has a voltage loss across it. Let's try another example. So here we have a 100-volt cell and 3 resistors. We notice they're connected in series, which just means connected in a row with no junctions in between. We notice as well that we don't know any voltages or currents, so we can't immediately do our deductive reasoning like we did last class. Instead, we first have to find the total resistance of the circuit. Once we've got that, we can then proceed to find the total current. So it's a series circuit, so the total resistance is the sum. So we add them up, 15, 5, and 5, 25 ohms. Now for the total current, our 100-volt cell, that 100 volts is going to be lost across a total of 25 ohms. So our circuit is equivalent to 100 volts and a single 25 ohm resistor. So the current then is just 100 over 25. We have 4 amps of current flow coming from the cell. Now we can do our Kirchhoff reasoning. Which means the voltage law and the current law. So with 4 amps coming from the cell, 4A, we see that there must be 4 amps flowing through each resistor because there's no junctions and no other place for that current flow to go. So just by KCL, we conclude that the currents are the same. We can then just do Ohm's law to get the voltages, V equals IR, across each of the resistors. Next, let's do a parallel circuit. Parallel circuits are circuits where resistors start and end at the same voltage. So that means they're connected at the top like these three are, and connected to the bottom with no other resistors in between. Those will be in parallel. Now in the second circuit, this resistor and this resistor are not in parallel because there's a one across the top branch there. So although these two resistors end at the same voltage, they don't start at the same voltage. So they're not in parallel. So what's true about a parallel circuit? Well, let's apply the voltage and current law. First, for the voltage law, we consider this loop. We know that the gains in this loop must equal losses, so the cell voltage must equal the drop across the resistor. We consider another loop. Well, the voltage gain in the cell is lost across the second resistor, and so on for the third. Now for the current law, we see junctions, so we know the total current is going to split up. A portion I1 will go on, then it will split up again into I2 and I3. Now at that junction, I2 and I3 will combine. So in this little wire here, we've got to write this slowly, the current flow will be the sum of I2 and I3. Then at this next junction, I1 comes in, and so what we've got here for our total current is the sum of those three, I1, I2, and I3. So we repeat the exercise to find the total resistance of a parallel circuit. Now by Ohm's law, R would be V over I. For algebra reasons, it's actually easier to find an expression for reciprocal resistance. So that's just going to be I over V. I total over V total. That's a T. We sub in the Kirchhoff result that the total current is the sum of the three currents. This is still all over Vt. We split that up into three separate fractions, and then we substitute in the fact that Vt is the same as V1, is the same as V2, is the same as V3, and then we recognize that I over V is a reciprocal resistance. It's the reciprocal of R1, 2, and 3. So we know that the reciprocal of total resistance is the sum of the reciprocals. If we want to solve that for total resistance, we just take, try and adjust this a bit for clarity. Okay, there we go, that's better. All right, now I gave myself some room. I need some room because it's going to be the reciprocal of the sum of the reciprocals. And that, of course, will have units of ohms. All right, so here's a simple parallel circuit. Let's find the total resistance and current, and then solve for each of the resistors. So we get a 60-volt cell, so we're going to have a 60-volt drop across this resistor. If you consider that Kirchhoff loop, there'll be a 60-volt drop across that one. Each of them gets a 60-volt drop. We use Ohm's law to get the currents then. 20 ohms, 60 volts gives 3 amps of current. 3 and 4 adds to give 7. Then the 6 adds in, we get a total current of 13 amps coming from the cell. So for the total resistance then, it's 1 over R1 plus 1 over R2 plus 1 over R3 reciprocated. So we've got 10, 15, and 20. So let's do this as an exercise in mental math. A 10th plus a 15th plus a 20th. The common denominator is 20, 15, and 10. The common denominator will be 60. So we have 6 60ths plus 4 60ths plus 3 60ths. That's 13 60ths. And the reciprocal of that is then 60 over 13 ohm units. So that's about 4.5. And then if we were to calculate the total current based on that, we take the cell voltage of 60 divided by this resistance and we get 13 amps, which of course is exactly what we found previously, just using Kirchhoff reasoning. Now, let's consider a mixed resistor circuit. This is a circuit that's neither simple series nor simple parallel, but is going to have a series or parallel part to it. So we need to recognize resistors in series or parallel. So we look at the circuit and ask the question, do you see any resistors in series or parallel here? Yes, these two are in parallel. They're connected to the top, connected at the bottom. They have the same voltage drop. In this next circuit, you may think that those two are in parallel, but they're not. But these three are connected in a row with no junctions in between. They're in series. Here we see resistors in parallel, connected to the top, bottom rather, and nothing in between. But then there's another pair of parallel resistors here. In this circuit, there's no simple parallel. There is, however, simple series. Two resistors connected in a row, no junctions in between. That's series. So by recognizing these series and parallel parts, we're able to simplify the circuit down to a single equivalent resistance, and then we have a basis for doing our Kirchhoff reasoning. Let's try an example. So here we have a mixed resistor circuit. We notice that we don't have any currents, so we have no basis for doing our Kirchhoff reasoning, our deductive reasoning process. So our step is to first find the total resistance, and then we'll know the total current. So we look at the circuit. Is there any resistors in series? No, because of the junction at the top. But we do have resistors in parallel. Yes, the 10 and the 15 are connected at the top and bottom with nothing else in between. They're in parallel. So we can reduce those to an equivalent just using the rule for adding parallel resistors. So it's a 10th plus a 15th. Common denominator is 30. That's 3/30 plus 2/30. That's 5 over 30. And then when you take the reciprocal, 30 over 5, those two together act like a single 6 ohm resistor. So we redraw the circuit at this point. It's still a 20-volt cell. We haven't done anything with the 4 ohm resistor. It's still there. But now we replace the two parallel resistors with a single 6 ohm. This drawing step is convenient in terms of making the solution more clear to read later on for studying, but you could just do it in your head. The next step is to realize that now the 4 and the 6 are in series, so we add those together to get the total or equivalent resistor. So our equivalent circuit, our equivalent resistance then is a total of 10 ohms. And we have a 20-volt cell. 20 volts over 10 ohms, we have 2 amps of total current flow from that cell. As soon as we have that current flow, we can now use Kirchhoff reasoning. There's 2 amps coming from the cell. Now we can go through and figure out what's happening with each of the individual resistors. So the 2 amps from the cell, well, all of it has to flow through that 4 ohm resistor because there's no junction there. So we know how much current is flowing there. So let's call that resistor 1. So we know the total cell current of 2 amps equals I1. So there's 2 amps of flow there. So that's R1, and we know I1 then for that first resistor is also 2 amps. Now, because we have the voltage and current, we could just do Ohm's law. 4 ohms, 2 amps, there's an 8-volt drop across that first resistor. Let's call that voltage 1. Now, there's a junction there. So that 2 amps of current is going to split up. So we know that the total of those two currents will be 2 amps, but we don't know right away how that 2 amps splits up. We do know that whatever I2 and I3 are, they have to add together to give us 2, though. So it looks like we're not going to make any more progress with the current law. So perhaps we should consider the voltage law. So the voltage law tells us that in this loop, the gains have to equal the losses. So we're gaining 20 volts in the cell, and we're losing 8 volts across the 4 ohm resistor. Then we have an unknown loss V2, but we end up back down where we started at 0. So the 20 volts is lost across resistor 1 and resistor 2. So now we know that we have to have 12-volt drop across resistor 2. That means we have to lose 12 volts across resistor 3 as well, because V2 will equal V3. And it's helpful at this point just to draw a nice summary diagram. So we know 2 amps and 8 volts there. We just found there's 12 volts and 12 volts across these two. We can now use Ohm's law to find the currents. I is V over R, 1.2 amps there. V over R, 12/15 is 0.8. And the nice thing about 1.2 and 0.8 is they add up to 2, which was the total current coming from the cell. And so we have a nice consistent solution.